Welcome to our 5G testbed in Nuremberg, Germany. Here in our testbed we work on new applications and new services enabled by 5G for industrial scenarios. And the new service that we want to focus on today is 5G positioning. 5G positioning comes in many flavors. It can be time-based, based on the signal strength, and also angle of arrival and departure of the signal can be used for positioning. What we want to show you today is downlink TDOA, time-based positioning in the frequency range 1. That means below 6 gigahertz in the frequency and 100 megahertz of bandwidth between 3.7 and 3.8 gigahertz. For this downlink TDOA position, we are emulating a UE on the HEV, and this HEV is tracked by the positioning signals that are transmitted by a total of 6 antennas that are distributed here at our testbed. One of the aspects people are most interested in with respect to positioning is, of course, accuracy. And based on our evaluation, we can say that the theoretical estimate of 20 centimeters that can be achieved in frequency range 1 for an industrial application is absolutely realistic. But of course, this will be an evolving process starting by lower accuracy and then going towards and near the 20 or even 10 centimeters. But of course, there are also other aspects that are important for positioning and that we are trying to evaluate here. Just think about your shop floor. Here we have a very nice scenario for positioning with a lot line of sight, but your shop floor may be more crowded and the whole scenario might be more complex. The environment is more complex. And this in general is a challenge for positioning. But luckily, I have a few colleagues, and I want to introduce you especially to my colleague Christoph, who is working on methods to make positioning not only accurate, but first of all, more reliable enough for industrial applications.
Thank you, Max. Radio frequency signals, no matter if we talk about LTE, 5G, or other proprietary systems, they are subject to perturbations as the signals travel through the environment all the way from the transmitters to the receivers. Signals get reflected, absorbed, or scattered, which leads to multipath propagation, which makes it very difficult for us to estimate a correct time of flight, which we need to estimate a position with multilateration approaches. While this is not a general problem all the way, because such situations are rare, we face them a lot more often in industrial indoor environment because of metallic surfaces and heavy machinery. This is why we heavily rely on machine learning techniques throughout our entire signal processing chain. We use machine learning techniques, in particular deep learning methods, for instance, to better estimate complex movement models of objects, to estimate positions directly from channel impulse responses, or also to do a channel classification or a more reliable TOA estimation. We can use such information in hybrid tracking or positioning filters, which will be part of what Jochen is telling you.
Thank you, Chris. Those hybrid signal processing filters can be used for 5G signals, but also for many other signals, like here in indoor environments, 5G signals or ultra-wideband signals, or in outdoor environments for GNSS signals from GPS or Galileo. In principle, we like to combine every kind of sensors, signals, and information that we have to ensure a robust and precise positioning. In use cases, for example, in indoor environments for robots, you could use onboard sensors like cameras, lidars, or inertial measurement units, and combine them with 5G signals to have an accurate position everywhere here in the facility. In outdoor environments, you could use, for example, a hybrid positioning for forklifts to ensure accuracy on the whole premise and so that you can find your assets anywhere. You have seen that with 5G positioning, machine learning, and sensor fusion, we ensure a high availability, robustness, and accuracy of positioning and enable many use cases.